This session we are going to discuss the economic aspects of power system such as connected load, maximum load, various reserves such as spinning reserves, cold reserves, hot reserves, etc. We will also discuss the factors affecting the cost of generation such as load curve, load duration curve, integrated load duration curve, load factor, demand factor, diversity factor, utilization factor, plant capacity factor, etc. in detail and the related problems. Okay, let us start. The first important term is connected load. Connected load, it is a sum of ratings of all load connected to the power system. That will include consumer apparatus such as fridges, washing machines, motors, lights, laptops, mobiles, etc. and also large rating equipments in factories. So sum of all ratings of these equipments is called connected load. Okay, the maximum demand, that means maximum power demand or maximum load. So load, power, demand, etc. will represent the same thing. Maximum power demand or maximum load. It is the highest load connected to the power system during a particular time. That time may be considered as a day or a month or an year. Then the third term is firm power. Firm power is a power that is always available, or it is a power intended to be always available. Then we have to discuss various reserves: cold reserve, hot reserve and spinning reserve one by one. First I am writing cold reserve. We can explain cold reserve as, suppose in a power station there are so many generators, but all generators are not always in operation or not always running, but that can be run depending upon the load demand. It is a reserve generating capacity available in the power station that are not in operation if demands it available for use. So it is a maximum generating capacity that is available in the power station or available for service, but that is not in operation. That is, all the generators are not running. If loads demands, can operate the generators or run the generators and power is available to supply the loads. So that is a cold reserve. So that is a maximum generating capacity available for service, but generators are not always in operation. Okay, next is hot reserve. The generators that are running or in operation but not available for the service. Not available for the service means that is not always connected to the bus, but the generator is always running or operating. If load demands, that can be given for the service. In cold reserve, all the generators are not running, but if demand, the generators can be run. In hot reserves, all the generators are running, but that is not available for service. If it needs, it can be available for service. Then next is spinning reserve. So spinning reserve means all the generators are running and connected to the bus, and that is available to take the load. So spinning reserve means generators that is connected to the bus and they are ready to take load. If the load demand is increased, then power is taken from the spinning reserve. These are the concept of this reserve. Now we are going to discuss the factors affecting the cost of generation. First is load curve. It is a plot load against time. That means the load on power station against time. So we can draw the plot as the y-axis that will represent the load on power station that may be in megawatt. So this is a load. This is against time. The time duration may be a day or a week or a month or yearly based. So with reference to time, the load demand is always varies. So that may increase, that may decrease and may reach the maximum, etc. I am randomly drawing a load curve like this. Suppose this is for per day. So what happens? Here load is increased, then decrease, again increase, decrease. So this will increase and decrease in fashion. the slope of the curve is, here the slope is positive slope. So for decreasing, here the slope is negative. Again here the slope is positive, slope is negative. Here all the slope is negative. So slope of the curve may be positive or negative in the case of a load curve. The load demand on the power station against time, that is called load curve, and the slope may be positive or negative, that depending upon the increasing and decreasing of the power demand. We can represent this by an histogram. Suppose I am drawing the load demand by using an histogram. This is the curve representing the load demand for a particular day. Okay, so during this duration of time, load demand is this much megawatt. This is megawatt 1. For this time duration, this is megawatt 2. And for this time duration, this is megawatt 3. For this time duration, the load demand is decreased, that is this. So this is a histogramical representation of a load curve. We can represent this like this. This may be the actual load curve. So we approximated this by using make of an histogram. During this time duration, the slope is positive, and during this time duration, the slope is negative. Since at night the load demand is decreased, and the daytime the load demand may increase. But at a particular time, the load demand reach its peak value. Okay, this is power against time. So what is the area under this curve? So we know that, suppose I am taking the area under this curve. So y-axis is power. So power into time. Power into time means energy. So the area under this curve will give the total energy produced. That energy in kilowatt hour. Since the power is in kilowatt or megawatt, time is in hour. This is a unit of energy. So area under the load curve will give the total energy produced. Energy generated, that is equal to load into time. So average load can be calculated by actual energy generated divided by time. That means average demand means load or average power demand, that is equal to actual energy generated during a period divided by number of hours in that period. So this ratio will give the average load demand. From this expression, we can obtain actual energy produced during a period, that is equal to average demand multiplied by number of hours in that period. That means actual energy generated during a period, that is equal to average demand multiplied by number of hours in that period. That is number of hours in that period. This will give the actual energy generated. That is average demand into number of hours in that period. Okay. Next is load duration curve. Load duration curve is nothing. It is a plot of load against time, but the load is arranged in a descending order. So we can draw the load duration curve as, here this is the maximum load. So I am drawing this first. Then second is this. That is the arranging in descending order. Then third is this load. And fourth is this load. And again this load. And this load. So this is arranged in the descending order. This is a load in megawatt and it is a time duration. So if I am arranging load in descending order, then it is called load duration curve. Okay, load duration curve. Here we can draw the shape of the actual load curve like this. Okay, to this maximum we have positive slope and negative slope. Look at this figure, we have only negative slope. So for a load duration curve, it has always a negative slope. It is obtaining from the load curve by arranging load against time in descending order. Next is integrated load duration curve. It is a plot load against energy generated. Okay, so the load in megawatt and the energy can be expressed in megawatt hour. Okay, suppose this is in kilowatt, then we can represent energy in kilowatt hour. When the load is megawatt 1, then the corresponding energy is represented by megawatt hour 1. When the load demand increases and when it becomes megawatt 2, then the corresponding energy is megawatt hour 2, and similarly megawatt 3 and megawatt hour 3 and so on. Suppose there is a change in load. Load is changed from megawatt 2 to megawatt 3. So this is the change in load, this much value. So what is the corresponding change in energy generator? So this difference that will give, that is MWH3 minus MWH2. This difference will give the change in energy generated. From this curve, we can obtain the change in energy generated when there is a variation in load. So that is an advantage of an integrated load duration curve. Suppose the load is decreases from this to this. The decrease in load is this. So the change in energy generated is the difference of these two. Next we have to define certain terms. First is load factor. Load factor is defined as a ratio of average load demand by maximum load demand. So its value is always less than 1. Since average demand is always less than maximum demand. Then what is the advantages of load factor? Suppose load factor of a particular power system is equal to 0.5. This implies average demand is only 50%. But we have always produced 100% so as to meet the maximum demand. So we have to produce 100% so as to meet the maximum demand. That will increase the cost of power generation. Suppose the load factor is 0.99. That means the average demand, that is 99%. We have to produce 100% so as to meet the maximum demand. But the average demand is very high. It will result in less cost of generation. So that is more economical. That is cost per unit will decrease if average demand is approximately equal to the maximum demand. Otherwise, for example here, the average demand is only 50%. The power system will meet the maximum demand. So we have to generate 100%. That will increase the cost per unit. So for a good power system, the value of load factor should be approximately equal to 1. That is the value of 0.99, etc. Demand factor. It is defined as a ratio of maximum load demand by connected load. Since the connected load is always higher than the maximum demand, so the value of demand factor is always less than 1. If the demand factor is low, that will result in less capital cost. That is less capital cost if the demand factor is low value. Next is diversity factor. Diversity factor is defined as the ratio of sum of individual maximum demand by maximum demand on power station. It is usually greater than 1. So if the individual maximum demand is higher, then that is an advantage for the power system. If the diversity factor is large, that means diversity factor is high or increasing, that will result in maximum demand decrease, installed capacity decrease and cost also decrease. That means this will result in maximum demand decrease. Installed capacity decrease. Installed capacity will decrease and cost also will decrease if diversity factor increase. This is utilization factor. It is defined as the ratio of maximum load demand to that of the installed capacity of the plant. It is always less than 1. That is always less than 1. If utilization factor is high, that implies maximum demand is high. So that results in maximum demand also high. Also high. Then we can say the power station is having proper utilization. That is, the power station is having proper utilization. Okay, so this is an advantages of power station. Then reserve capacity. Reserve capacity is the difference of installed capacity and maximum demand. Reserve capacity is equal to installed capacity minus maximum demand. Suppose if reserve capacity is equal to 0, that is RC is equal to 0, that implies installed capacity is equal to maximum demand. So this implies installed capacity is equal to maximum demand. In such cases, what happens to utilization factor? Both maximum demand and installed capacity are equal. So utilization factor is equal to 1 if reserve capacity is equal to 0. Now capacity factor, it is defined as the ratio of average demand by installed capacity. So capacity factor is equal to average demand divided by installed capacity. Suppose I am multiplying the numerator and denominator by time. That is average demand into hour and installed capacity into hour. So average demand into hour means actual energy produced or actual energy generated. Installed capacity into hour means the energy that can be produced during that time. This is equal to actual energy produced or generated. That is actual energy generated divided by maximum energy that could have been produced. Could have been produced in the power station. Now we can manipulate the capacity factor as this is equal to average demand. We can write divided by maximum demand. Okay. Now so as to balance the equations, this into maximum demand divided by installed capacity. Average demand by maximum demand. This is called load factor. And maximum demand by installed capacity. That is called utilization factor, UF. We can define capacity factor, that is a product of load factor and utilization factor. Next is planned use factor. The planned use factor, that is defined as the station power output in kilowatt hour. That is the power generated in the power station by planned capacity into hours of use of plant or hours in which plant is in operation. Planned use factor is always more than or equal to planned capacity factor. Planned use factor greater than or equal to planned capacity factor. Okay, in this problem we want to find the demand factor and load factor. Options are given. So we have a generating station having a connected load of 550 megawatt. So connected load is equal to 550 megawatt, and the maximum demand is given as 380 megawatt. That is maximum demand that is equal to 380 megawatt. Then the next data given is the number of units generated per annum. Per annum means per year. That is 20 into 10 raised to 8. So, number of units generated per year. Units generated per year, that is equal to 20 into 10 raised to 8 units. So these are the given data. We want to find demand factor and load factor. Maximum demand connected load. So demand factor is equal to maximum demand by connected load. That is equal to maximum demand, that is 380 megawatt. So 380 megawatt divided by connected load. Connected load is 550 megawatt. So 380 divided by 550 megawatt. That is equal to 0.69. So demand factor is 0.69. So average demand, that is equal to number of units generated per year divided by number of hours in a year. So that is equal to number of units generated, that is given as 20 into 10 raised to 8 units. So 20 into 10 raised to 8 units divided by number of hours in a year. That is equal to 8760. So this is equal to 228.31 megawatt. Now load factor, that is equal to average demand by maximum demand. That is equal to average demand is 228.31 megawatt divided by maximum demand, that is equal to 380 megawatt. So this is equal to 0.60. So option A is the correct option. Demand factor is 0.69 and load factor is 0.6. In this question, we have a power station as a maximum demand of 1000 megawatt and annual load factor, that is given as 70%, and plant capacity factor, that is given as 60%. We want to find the reserve capacity. Okay, so from the given data, the maximum demand is equal to 1000 megawatt. Load factor, that is equal to 70%. So that is equal to 0.7. And this is the annual load factor. Now, plant capacity factor, that is given as 60%. So that is equal to 0.6. Load factor, that is equal to average demand divided by maximum demand. From this equation, we can find average demand, that is equal to load factor into maximum demand. That is equal to 0.7 into 1000. That is equal to 7. Capacity factor, that is equal to average demand by plant capacity. Therefore, plant capacity, that is equal to average demand divided by capacity factor. This is equal to, so 700 divided by capacity factor, that is equal to 0.6. So 700 divided by 0.6. This is equal to 1166.6 megawatt. Now, reserve capacity, that is equal to plant capacity minus maximum demand. So this is equal to plant capacity is 1166.6 megawatt minus maximum demand. Maximum demand is 1000 megawatt. So this is equal to 166.6 megawatt. So approximately equal to 167 megawatt. So option C is the right answer. This is a general question. Which of the following generating station has minimum running cost. Options are given: hydroelectric, nuclear, diesel and coal. Since for a hydroelectric power station there is no fuel, fuel is only water. So running cost is minimum for hydroelectric power station. This is a general question and also a previous year gauge question. For a hydroelectric power station with an head of 60 meter, then which turbine is used? For a high head, Pelton turbine is usually used. So 60 meter is a high head. So Pelton wheel is usually used for this generating station. In the next session, we will discuss about power system representation and per unit quantities. Okay, thank you. Bye.